The next presenter is Sooraj Nair. He's from Arizona State University. Go ahead and take it away.
Hello, everyone. My name is Sooraj. I'm a PhD student from Arizona State University in the School of Sustainable Engineering and Built Environment. This presentation will focus on part of a work that we have done on fiber reinforced mixers that we have used for 3D printing. We will specifically be focusing on the effect of layer height on the crack propagation and fracture parameters of the fiber reinforced 3D printable binders. So mandatory introductory slide. Several works, like using non-fiber and fiber reinforced mixers have been used in small scale as well as large scale segmental bridge constructions. So this is just an overview, one from our institute as well, where we have just printed small scale elements. But the point that I want to put forward is most of these are focused on layer wise material extrusion and stacking. Although there are other studies which do powder based printing as well. But this whole presentation will be focusing on material extrusion, and this is a typical printer that the printer that we have used for this study. It's a gantry based one. Dimensions approximately 1.5 meter in the XYZ directions, and we do have a print head onto which a mixer pumps the material, but most of the time we directly feed the material into the hopper. And then it's been controlled by a stepper motor with a screw extruder that extrudes the material to print, mostly limestone and OPC based printable motors in our case. So just a brief background or overview on several other studies which is on the basis of which this particular study has been derived. This is a very good overall flow of parameters in printing from Seattle. And we'll be more focusing on the material and the printing process side, that mainly because on the material side we're introducing fibers and how that is influencing the printed hardened properties, and in the printing process side layer height is a major parameter, and how does that affect the post output mechanical characteristics of the question. And that's two main factors that we'll be focusing on here. And there's several other studies which have reported weaker interfaces or relatively weaker interface region due to drying or due to improper laying, which can affect your output strength. And because of these layers as such, generally when we report the mechanical properties, we do because of the anisotropy, we do the testing in three different directions. But for the sake of this study and within the scope of this study, we'll be only looking at orientation number one along the direction of the vertical printing. So as far as the experimental plan is concerned, what we do is we have a nozzle diameter which is 20 mm in 20 mm diameter nozzle, and what we do is we take a typical filament which is having a layer with LW and a layer height LH, and we take values as a fraction of the nozzle diameter. In this case, and in this study, we take 25%, 50, and 75% of the nozzle diameter as the layer height. So it will be 5, 10, and 15 mm in this case. And then the layer width is kept constant at around 1.1 to 1.15 times the nozzle diameter. So typically it will be around 20 to 22.5 mm. So when we vary these layer height, what we do is like varying the layer height and then checking how the post-print hardened properties are. And specifically, we'll do flexural testing and mostly 4-point bending and 3-point bending. We have an ongoing study looking at the compression effects as well, but for this presentation, we'll look at the flexural properties. Now, what we do is we print slabs at these different types of layer heights, and we do it for non-fiber and the fiber reinforced condition. The fiber reinforcement is 0.2% by volume of the overall mortar that we're using. and then we cut them into beams of approximately 3 by 3 cross section, and then for roughly around 4 times the depth as the span, and we subject them to 4 point bending for the flexural strength, and then 3 point bending with a notch case to understand the fracture properties. So, of course, after printing, we have to check how the integrity of the printed beam is. And when we slice them to look inside, we see that, again, when we increase the layer height, there are more defects introduced. This is, again, typically reported in literature. Although we made sure that visually the filaments are overlapping while printing, and that, visually we don't see any gaps as such. We do see that between the filaments there are gaps, and that tends to be happening more when you increase a layer height, and that tends to be happening in both the non-fiber and the fiber reinforced case. So taking a closer look at a lower layer height, like the LH5 case, so the first image is a non-fiber and the second is a fiber case, we see a few micro voids along the interfacial line, which is marked by this yellow line over here. The point where I stopped was, so we have a non-fiber case and a fiber case at 5 layer height. So along the interface, we do see a micro post present, which is typical because you have two different layers being laid one over the other. So there's definitely going to be a few air voids in there. But in the case of a fiber reinforced specimen, we do see that the fibers are sticking, like typical fibers being shown. There are voids that encompasses those fibers, or there are voids which are, predominantly seen around the fibers. And along with that, we do see a few micro cracks in the fiber reinforced specimens as shown in these images over here. And then another case over here where along the fiber, I mean, not exactly around the cross section of the fiber, but in the vicinity of the fiber, you see another void. So that tends to ask us is there something happening when you are incorporating steel fibers in this case while printing? When compared to other fibers, or when compared to a non-fiber reinforced case. So so the next step was to test them under flexure. So in this case, for a 4 point bending case, what we see is when you have a layer height, when you go from a smaller layer height to a higher layer height, and this gray one is for the non-fiber specimens, you tend to see that the flexural strength reduces, and that's attributed to the larger number of defects that is incorporated when you have a higher layer height. But in contrast, for the fiber reinforced case, you tend to see an inverse relationship. Like for the lower layer height, you see a relatively lower flexural strength, and this in connection to whatever we saw in the last slide with the microscopy images. What we have noticed while in printing as well is when you have a steel fiber which is much stiff and rigid, and your layer height is much lower than the fiber length. So this is a typical fiber, and this is to scale, and this is the layer height in comparison to the length of the fiber. But the fibers tend to be dragged and scratch your interfaces to form more voids and voids around the fiber. So fiber to matrix bond becomes also weaker. And as you increase the layer height, the chances for that scratching and the dragging of the fibers, which causes defects in your printing, are much lesser. And you tend to see a little bit more better characteristic when it comes to the flexural strength. So the overall average flexural strength is much higher, definitely with adding fiber reinforcement, almost 30-60% higher. But then there tends to be there seems to be fiber to layer height incompatibility. Um, and then what we do is we go for the 3 point bending case with a notch specimen. And specifically in this case, because it's a fracture characterization, we do a cyclic loading instead of a monotonic loading that we do in a 4 point bending case. And this one is for a non-fiber and versus a fiber. And there is significantly increased residual strength for the fiber reinforced specimens. And using the unloading compliances and the 2-parameter fracture model TPFM, we calculate the fracture toughness and the critical tip opening displacement. And generally, we don't see much of a difference for these two parameters, although like KIC, there is a marginal reduction in the case of a non-fiber reinforced specimen, but the critical tip opening displacement is more or less similar. But when we calculate the fracture energy release rate, that tends to be much more sensitivity when it comes to layer height as well. So for a typical LH, like layer height 5 to 15 comparison is given over here, where a non-fiber versus fiber specimen show almost 2 to 3 times higher fracture characteristics for a lower layer height, and for a fiber reinforced specimens, fiber reinforced specimens show 2 to 3 times increase, and versus the non-fiber specimens. And if we calculate the inelastic and elastic part of the fracture energy release rate, you do see a much higher inelastic strain energy release rate in the case of fibers, because the fibers tend to bridge the cracks. Although the elastic portions are more or less the same, or it's not too different when it comes to the overall fracture energy release rate in the case of fiber reinforced specimens. So fibers definitely really helps in higher strain energy release rate, and this is what we have to think in this is, when you have a larger number of interfaces, each of those interfaces act like a crack barrier or an energy dissipation medium. So when there are larger number of interfaces, when you choose a lower layer height, your strain energy release rates would be much higher, and some of the results using digital image correlation is to follow. So, like I said, we have seen that cracks tend to deviate along the interfaces as shown over here. And I mean, if you have weaker voids, then it tends to branch into those voids as well. But we also see crack branching along the interface, and typically, eventually they join in front as well. This is a case where in a 4-point bending case, you see that along the interfacial lines, you tend to see that the cracks change directions much significantly, instead of proceeding in one particular direction, which also shows that layer interfaces acts as crack barriers. Now, to visually characterize this or observe what exactly is happening, we also did digital image correlation on the flexural specimens, and in this case it's for the 3-point bending case, and you can see the notch in each cases. And first is the 5 mm layer height, and as you go down, it's the 15 mm layer height. And I've shown images from different points in the loading cycle, like this is 50% peak, 90%, and the peak, and beyond the peak with the first unloading point and the second unloading point. Now, what we see in this case for a non-fiber specimens are you tend to see a much earlier formation of fracture process zone when you have a larger layer height. And then once the peak or near the peak has formed, you can see that the fracture process zone that is formed in a lower layer height is much more sharper and is much more longer when compared to the other layer heights. And this is mainly because you have in this particular length itself, let's say for a typical 15 mm length in front of the 15 mm notch, you have 2 to 3 interfaces in case of a layer height 5, versus in case of a layer height 15, you have like one layer interface. So the energy needed before the crack starts to pick up to form and propagate is much higher, as shown earlier in the previous slides, and that's what we see in the DIC case also. So that's really interesting. When we compare it to the fiber reinforced specimens, we really don't see much of an effect in the post-peak case from what we see in the non-fiber specimens, and that's mainly because the fibers in the post-peak region gets active, and the fracture process zones look more or less similar in the case of fiber reinforced specimens. Although for the LH5 case in the fiber, you can see that the fracture process zone was much smaller, and that is in continuation to the lower strengths that we saw in the case of the flexural strength for layer height 5 fiber specimens. Now, the crack extension, when we calculated using the 2-parameter fracture model and we plotted with respect to the load, you can see there is a significant difference in the energy that the specimen could actually carry with respect to the crack extension. So, for example, like for a 30 mm crack extension, you have almost a 25% increase in the increase in the load that it could take at that same crack extension for the fiber reinforced specimen. So adding fibers is definitely beneficial, and it's possible to use. And if we use the DIC to find the crack tip opening displacement and plot it with respect to the crack extension, you could see that the tip opening displacement moves much more faster in the case of non-fiber specimens with respect to the crack extension, whereas it's much more lagged and delayed, and it shifts to the right for the fiber reinforced specimens. And these points or these lines are corresponding to the critical crack tip opening displacement calculated from the two-parameter fracture model. And you could see that an LH5 critical tip opening displacement is generally a little bit more higher than the LH15 case, or more or less the same. But it tends to shift in the case of fiber reinforced specimens when compared to the non-fiber reinforced specimens. So in summary, from whatever we have observed, when we vary the layer height, when you increase the layer height if you're not using a fiber reinforcement, what we tend to see is a reduction in the flexural strength. But if we can add fibers, that tend to improve and restrict the influence of the layer height is what we want to put forward. Now, these layer interfaces act as the crack barriers and improve the fracture response. So they are weaker when compared to the bulk, but how much weaker is a question, and it has to be characterized, which is not covered in the study. But if you have a proper nozzle pressure and these layers are laid with that pressure, there are chances that the interfacial strengths could be not that different from the bulk, but it's relatively weaker, and which is advantageous in terms of the fracture resistance of the specimen. And when we use a fiber, this is a major takeaway from the study, that especially when we use a stiff or rigid fiber like a steel fiber, there is a possibility of having a fiber length to a layer height incompatibility that could be detrimental to your printed structure. So it is always recommended, at least for rigid fibers when used, to choose a layer height which is relatively higher than the fiber length that we are taking. So in this case, it was 13 mm fiber, and we could see that a 15 mm layer height was much better when we are using steel fibers. And these results are not, at least with the results from this scope of the work, not applicable for flexible fibers like polymer fibers, but specifically for steel fibers, this is really important. So with that, I conclude, and I'm welcome to take any questions.
Thank you. So I see one question, and I think you did answer this in the presentation, but did you cut specimens from, it says, did you cut specimens from layers? I assume that means printed samples. And then I have a follow-up question for that. From me, these ASTM, like an ASTM standard has pretty stringent parameters in terms of dimensions and out of planeness. How did you ensure that the specimens were planar when you cut them?
Okay. So what we used was a normal tile saw to cut the beams out of these slabs, and like I said, there were a little bit of dimensional tolerance that we had to actually give when we are actually targeting for a 75 by 75 cross section. We have tried to keep it as much as possible to be within that dimension, but if there were 1 or 2 mm differences, we actually measure them and incorporate them in the calculation that we are making later. But otherwise, as far as the cutting is concerned, one surface is always flat for us. Like when we print the slab, the base is always flat. So that is a reference surface, and we put that surface first on the plane of cutting, which is the platform which is moving under the cutter, and then we make the slices linearly. And once those cuts are made, now we have two planes which are perpendicular and planar, and then with reference to that, we do the subsequent cuts, so that we make sure that the cuts are all in line, and there is not too much deviation in the beam dimensions. If that answers the question.
I think so. Yeah. So we have one more question. Why was layer height chosen among other structural parameters to study fracture? Can you comment on the elastic versus inelastic portion of the characterized fracture energy?
Sure. So, so this was again just a starting point to look at the fracture parameter. So among all different parameters, we wanted to select a process parameter which could actually kind of is more influential in the actual printing process. For example, in the case of layer height that we have chosen, like it's always a question what layer height to go to, because that will define the time taken for printing. So if you go for a lower layer height, the time taken for printing would be much higher. Of course, you could argue that you can increase the print speed, but when it comes to the fine points in your printing or the structure or the design that you have, you might still want to like lower the print speed. So it's always beneficial to go for a higher layer height generally. But then that is where we ask, okay, so if you want to go higher, like, how do you like does that make a difference in terms of the hardened properties? And will that also, have an effect when with the fiber lengths that we are choosing? So that's how we chose that and went for layer height as a first step for the study. And then as far as the elastic and the inelastic portions are concerned, I mean, it's pretty, obvious, I would say, that the fiber reinforced specimens generally would show a higher elastic and inelastic energies, but how much does it, as a percentage, how much does it increase? And like in this case, we have chosen a very small amount because we do have, and everyone knows that there is restrictions when we are in rheology, we are using fiber lengths, right? So, but at 0.2% itself, we could see a significant amount of increase in the elastic and inelastic properties. So that I think is like important, and I think that answers the question which was asked.
Thank you.